Very warm welcome to our session. Which is on the topic a new way of testing in the autonomous factory. We tried something on the simulation-based testing. We'll just start with it. My name is Vinayak Rout, and I, along with my colleague Pratik, would like to share the result and also the experience that we got while working on this topic. So basically, we are working in Siemens, and in particular, the business unit is factory automation, and which provides or offers the automation solution for the factories. So it can be of small size, bigger scale factories. So maybe just to introduce Siemens, so we solve the automation challenges here, particular to in factory automation with our broad product portfolio. So the very well-known products may be the PLCs, 1500, 1200 PLCs to control the process. And we also have human machine interfaces like HMIs to visualize the process. And for the engineering purpose, we have the TIA portal, which is very well known in the engineering world also. So this is how we work. This is what we do the business. And so let's have a look into the future. What is the vision of the DIFA? So our vision is to go from automated factory to autonomous factory. So in this case, we just need to first see what is the difference between this autonomous factory and automated factory. So basically, automated factory is a rule-based factory. So we write rules like if and else rules. So if I want to give an example of it, so you can consider a maybe a Coca-Cola bottling plant. So you might have seen in different videos that bottles will be coming in a sequence way at a particular position. Then the cap will be placed on top of it, and then it will be released. So you think this situation. So every time the bottle has to be at the same place with the same orientation maybe, so it should not be tilted or some other way positioned. So in that case, what will happen is it may reject the bottle, or maybe it may improperly fit the cap on the top of the bottle. So this is what happens in a automated factory, because everything is written in a rule based way. So where we want to improve here is autonomous factory. So the autonomous factory goes one step further. It is based on the automated factory, but it add few characteristics to it. The machines are self-learning system, and most of the machines, the behavior is trained, not programmed, and they are self-organized. So they plan and control the production process by themselves, and they take their own decision. So maybe no manual intervention or very small manual intervention is required over a longer period of time. So this is what our goal or our future is about. So maybe I think Pratik, you just started the video a little early. Can you just take it to the first initial part? Yes. So I just want to show you this small video to show the autonomous factory example. So I have taken a toy robot autonomously manufactured, because it has some similarity that the use case we are going to present today. So what will happen is the from the order entry to delivery of the customer, all work steps will be done very autonomously. So so we are now, you can see we are not out the assembly step. All parts are available. So now the job is the robot should pick up the individual parts of it. So robot is very much intelligent to pick up the body first, and maybe then the legs of it. So that it has taken some autonomous decision over here. But now when it is going to pick up the arms of it, so it is getting confused that which is the left arm, which is the right arm. So maybe for this instance, somebody, maybe manual intervention is required. Somebody needs to explicitly tell that okay, this is left arm, this is right arm. But then what will happen is maybe the autonomous system will retrain its intelligence systems or recalculate the things, and then it will learn by on its own. Maybe the next time it will not face this kind of situation. So now at the last, as the last step, the arms are placed on the robot, and the robot is ready now. So this is what we were trying to do. So everything will be automated here, and mostly this will be backed by many intelligence systems. So this is what our autonomous factory will look like in future. So this autonomous factory is basically a lot of puzzles are there. So FlexGraphs is solving one of the puzzle. So maybe Pratik, you can go to the next slide. So with this FlexCraft as the vision of autonomous factory becoming reality, one of the puzzle is getting solved here. So have a look at this video. Some robot is picking up the object. So you can see there is a bin and few objects are randomly placed in the bin, and a robot arm is picking up the object. So there is a depth camera. Maybe you can see it on the top of the video. So the depth camera, what it does is it takes the depth images and it sends to the FlexGraphs application. So this FlexGraphs application is a intelligent system. So some AI models are running behind of it. So what it does is it looks at that depth image and try to calculate a grasping point for a particular object. So when it gets, so it provides few information to the robot controller, and then the robot controller picks up the object. So this is the whole application, the FlexGraphs application, how it works. So basically if I want to give little more detail, so basically this is not a object recognition model. So rather the model is trained based on the surfaces and the texture of the object, because in the world there can be a millions of possibility of different kinds of objects. So that's the reason it is not a object based or object recognition model. Rather it is just a surface and texture based model, so it can handle any kind of object. So when the colleagues of FlexGraphs consulted with us that how can we support them for testing. So initially we got some starting situation that we have written here. The first one is how to achieve high test coverage. So we need a high number of robotic cells, the way you see here, to with which the tester can run the test manually. So in the beginning they have started testing it manually. So for this they had to set up complete hardware setup and then they can test it. So that is one thing. So in this case how to achieve high test coverage, so we, because we need a lot of hardware components here. And there is no test automation, because all the test activities must be executed manually. So from setting it up, from placing the object, and then maybe if the robot cannot pick up some object, we can pick up the leftover things or reset the things. So those things are completely manually. So there is no test automation possible. So with no test automation and also with high number of robot cells, we could only achieve a low variance of test scenarios, because we want to test it thoroughly, then we need a lot of test scenarios. But with manual testing it is not possible with all the hardware. So this variance is actually very necessary and important for the testing, and which is not possible in this case. And all these things also increases the feedback time. So whenever the testing team does some testing, then it takes a lot of time to do things manually and give the feedback to the development team so that they can rework on their things. So the feedback loop is very long here. And then the third thing is, if we want to suppose retest the bugs to maybe suppose we found some defects or maybe some discrepancy in the behavior of the model, then if you want to reproduce it, how to do it. So if in case of manually placement or by a human being, then it is very difficult to note down everything and all the results of it. So it is very difficult to uh, reproduce the things. So similarly, also for the test coverage, how can we calculate test coverage here? So it is kind of not possible, or there is no chance we can calculate test coverage. So with this kind of starting situation, then we try to set a few goals that we can achieve. So or maybe to solve these test challenges. So first one, the reproducible test scenarios. So there should be some way we should reproduce the scenarios in a simpler way, so that we can run it identically at any point of time. And we should automate the test scenarios so that it can reduce significant manual effort. And then the high scenario variance, so it is necessary to achieve high variance in the test scenario so that we can cover as many customer use cases as possible in a particular time frame. So then coming to the test coverage, so it would be excellent to get a reliable and measurable statement for the test coverage, so that we will know what we are doing. send the running the test independent of the hardware. So this is something very important when we thinking of going in a simulation way. So the robot cell, first of all, it is very expensive, and also sometimes it is very risky in case of testing cases. So we need a solution which should do everything without a hardware component. And with all this, we also need to, as I mentioned, to shorten the feedback loop from our tests. So that is also one of the goal we have set in the beginning. So what we did after that is, so we tried to transfer the test execution from the real world to the virtual world. That means the complete test runs in a virtual and synthetic environment. So we solved these challenges with a game engine. So we conduct a small proof of concept of 3 to 4 months, and we did a working model of the thing. And my colleague Pratik is going to explain in a detailed way by playing a short video for you, and with that he will explain the complete workflow as well. So over to you, Pratik. Maybe I think he needs to be highlighted. Yeah. We cannot hear you still, Pratik, and even we lost your screen.
Hello, can you hear me now?
Yes,
Yes, we can.
Sorry. Um,
maybe you
yeah,
can share your screen one more time.
you can see my screen right now.
Not yet.
No, okay.
I think it is coming. Yes, it was there, but it
Okay,
has
I
disappeared.
am just resharing. Yeah, hope my screen is visible now.
Yes.
Okay. Okay, thank you, Vinayak, and sorry for this delay. Uh, So here, as Vinayak was mentioning, the objective for us was to create a complete simulation for our use case, that is the flexible grasping of objects based on artificial intelligence. So we created a complete and dynamic simulated environment for the FlexGrasp application, which will provide this AI-based system the necessary data to be tested, and also for the validation of the AI prediction. So this simulated environment we have designed using a game engine, that is Unity. So Unity is a popular game engine for prototyping everything from games to interactive visualizations. So in Unity, we work with something known as scenes. In these scenes, you can add all the 3D models for the real-time objects. So as you can see here, we have a robot table and a bin. So these 3D models, they can be instantiated in our scene in two ways. One is the static way and other is the dynamic one. So the robot table here is a static item, which means it is loaded beforehand and it is present in our application before we run it. And then there are dynamic elements, which can be the bin itself. It can be the robot arm, or it can be the items that are loaded in the bin. So these are all the dynamic elements. Uh, So for our simulation, we use a scenario configuration file as a prerequisite. So inside this configuration file, we have defined various parameters such as the position, rotation, scale, etc., which are used for loading these items dynamically. Um, so so this is how our UI screen looks like before running our application. So in the top part, we you see that there are many different buttons in the, and in the bottom we have few different tabs. So the basic flow of our application is, so first we provide a scenario configuration file as a prerequisite. Then we click on this calibrate button. So this calibrate button, it calibrates our scene in Unity with the FlexGrass application which is running. um, then we click on this test button. So this test button, first it captures two images. So one is an RGB image and other is a depth image. Then it makes an API call to the FlexGraph, which provides this. So which in turn the FlexGraph application will provide us a pick point as a result. Then we use this result from the FlexGraph to do our test. So this is our basic workflow. So here, as you can see that once we run our application, the bin and the items in the bin are instantiated at runtime. Uh, they are instantiated at runtime, and and then basically there are three ways of placing the items in the bin. So one is the manual placement, where we need to specify um, the placement properties inside the configuration file. The second is the random placement that you see here. So these are the options we provide for the item placement. So as we see in autonomous factories, that there are different kinds of bins arranged. So it can have a lot of items placed randomly, or a very chaotic bin with a lot of items which are scattered. So with this random placement, we enable this option. And then the third way of placement is the stack way of placement. So here in this option, we provide a way where we can stack the items on top of each other. So here, as you can see, the items, they are all placed on top of each other. They are all uh, calculated and placed automatically and optimally inside the bin. Um, so these are some of the ways that we place the objects in the bin. Then next is the handling of noise. Uh, so a challenge in our simulation with respect to cameras is the handling of noise. So as we can see that in the images that we have captured in our scene, so this is an RGB image that we capture from our scenario, and then this is a depth image, which is where this is a clean depth image from our scene. So here, as you can see that there is mm, little to no noise present in it, but in real time cameras there is often a noise component associated with it. In our use case, which is the FlexGrass application, it uses an Intel RealSense camera. So it was important for us to also simulate the noise from the camera to bring our simulation more close to reality. For this, we contacted a few image processing experts, and we derived a custom algorithm which generates noise specific to the Intel RealSense camera. So so for this, here we in our application we have provided a simple toggle button. So once we click on this toggle button, this button gets enabled, and if this toggle button is enabled, then we simulate the noise as a part of our testing process. Mhm. So this is how our generated algorithmic noise looks like. Uh, then then the final part of our workflow is running our tests. So once we receive the pick point from the FlexGrass application, so we do different levels of testing. So at the first level, we verify whether a pick point it is lying on the surface or not. So for this, we make use of the mesh of the 3D models. So with this mesh, we derive a kind of a 3D bounding box. So this bounding box for us is nothing but a ground truth or a test oracle. So you can think of it like in person detection systems where we draw a rectangle around the person identified. So as we are dealing with 3D objects here, so we plot a 3D mesh of the object and use it as a test oracle to identify more accurately and more precisely that whether the pick point is coming on the surface of the object or how far or how away it is from the surface. Uh, then at the next level, we identify the approach angle for the suction gripper. So so in our use case, which is the FlexGrass application, it uses a suction gripper for picking up the object, which in turn it uses air pressure to lift the object from the surface. So here um, we make use of the physics engine of the Unity. Uh, Sorry. So we make use of the physics engine of Unity to do a raycast. So here a raycast is nothing but a ray of light that we project from the position of the gripper, and then we do a few mathematical calculation to find the angle between the normal vector and the tangent. So in the end, we actually get an approach angle, and then we verify whether it is exceeding 20 degrees or not, as it is the maximum approach angle that is defined for our use case. uh, so this is the second level. We do the test, and then at the third level, we verify whether the pick point, whether the pick point is makes a proper seal formation or not at the position where we get the pick point. So here we try to identify for any gaps that the suction gripper creates when it comes in contact with the surface of this object, and or any other interventions. So so we fail the test if all these checks are not satisfied. So once all these tests get passed, we are ready to lift the object and move to the next item. So here we are not using any robot arm, so rather we are only using a suction gripper for our simulation. So we have only animated the picking of the selected item with the gripper. So so this completes one cycle of our test process. So this process is then repeated for other items till the bin becomes empty, and in the end we generate a complete test report. So this is our basic workflow of our solution. So so let us see next what all are the what all have we achieved from our solution. So over to you, Vinayak.
Small video what we saw there. So with that, we were able to achieve few of the things. So the first one is reproducible test scenarios. So here, as Pratik mentioned, so every scenario is defined in a configuration file for us. So in that configuration file, we exactly mention the properties of the each of the object, maybe the bins properties also. Maybe the bin can be rotated as well there, and the objects can be rotated also, positioned in a different way. So all those dynamic things we can do in those configuration file. So that configuration file we can rerun it at any time and it will reproduce the same thing. So there is also a option that we saw that Pratik also has presented, is the random placement, just to replicate the chaotic bin. So in that case also, suppose we randomly place something and we got a very good scenario and we want to retest it. So in that case also, we have options to save that scenario and in a different configuration file, and that can be rerun. So in also in case of failures, we can just save that scenario and we can rerun it. So with this, we got to know about the reproducibility of the test scenarios. So that is one thing. And then the test executions, it is completely automatic, and it can be run without any human effort. So we just need to create the configuration file, provide it to the simulation tool that we have developed, and it will run the things. And also we have given few more options now, like number of cycles. So maybe we just want to create a lot of chaotic bin and rerun the cycles, so that also is possible from our side here. And then the high test variance. So with this solution we can achieve a very high test variance in our scenarios. We can program to simulate almost all possible objects and combination of the objects with respect to its placement and orientation, and also the orientation of the bin. So everything is possible and reproducible with this solution. And then running the test independent of hardware. So our test is completely in the virtual world and does not need any dedicated test hardware like a robot cell or anything else, or it can just run in a normal machine, normal PC. And with the solution, we got very fast feedback loop from the test execution. So we can scale the feedback speed, and if we spend little bit on more on the computing power, then also we'll get more faster feedback here. And then the measurable test coverage. So this is something we have not achieved still, so we are currently working on this topic. So this is still open topic for us. And the last one, which also Pratik had mentioned about the virtual world, was too clean for us, which is not which does not happen in the real world. So there also we try to fill that gap with our noise generation mechanism, and that is also working for us now. So with all this, what kind of impact that we are bringing to our products? So the first thing I can say, to increase the test efficiency. So we are able to increase our test efficiency from the manual way of doing to our the current solution what we have implemented by a double digit factor. And but still we believe that the current factor is not the upper limit, and this is just a product of a proof of concept. So there is more possible to it, and maybe in future, near future, we'll work on it. And with the fact that we can run many more test scenarios in a shorter period of time, so we can then increase the confidence in our product as well. So these are the two impacts, major impacts we brought to the product. Maybe next slide, Pratik. So then how does the customer benefit from our solution? So maybe as we all know, one of the main tasks of testing to generate information so that our stakeholder can take some decision. So with our solution, we support the FlexGraphs team with a lot of valuable information, which enables them to make a go or no go decision for their release. And they can find a lot of critical critical use cases where their application does not work, and they can maybe retrain or rework on that intelligent model. So at the end, this also improve the product quality and increase the confidence in our products. So these are the customer value that we brought here, and then the business impact. So in my point of view, the quality assurance or the testing of products with AI component is a key technology and key capability for the future maybe. So with this know-how, we are with or without this know-how, we are not able to give a reliable quality statement to our customer. So if we give, then it will increase the trust in us from our customer point of view. So with this kind of future, we just started, and we hope we will achieve a lot of progress to it, and that's what we are hoping currently. So yes, so that's all from our side, and thank you for all your attention. And maybe we are ready to get some questions, definitely. But for now, maybe we show our contacts here. Maybe you can also contact us directly in future. So maybe I just saw one question. So what is the driver package used to connect to Unity to play for your use case? So I believe you meant is what how do we integrate our simulation tool with our FlexGraphs application. So the FlexGraphs application exposes few APIs with which we communicate, and so basically it is a REST API communication.
Okay, so thanks, Pratik and Vinayak for the presentation, and thanks for the time. As of now, we don't see any more questions coming in, so